Hello, my name is Tommy Wood. I'm an independent researcher into physically comparable discrete systems. I'm making this video to try and explain what my research is, the specific system that I'm looking into and have been researching, and to share a little bit about why I'm looking into this specific system and some of the details involved in this system. So recently there's been quite a few developments in the areas of discrete systems and looking at how the dynamics that emerge out of these systems might correlate to physical systems. For example, the Wolfram Physics project, which has shown some interesting compatibilities of the Wolfram model, or the discrete network systems, to special relativity and quantum mechanics. So now the Wolfram Physics project investigates many different rules, with the idea that taking a broad approach, we might be able to, with some targeting, find a system that creates dynamics that corresponds to something that is very similar to the behaviour of our own universe. But it's difficult to know exactly what rules to go with and what system to look into. So now, before the Wolfram Physics project, I have been working on this system that I'm going to go into today for quite some time, and I want to sort of explain right now why I'm looking into this system and what is incorporated within it. So you can see here on the screen at the moment there are some videos that I've made of the simulations that I've created. The ones at the bottom here I actually created quite a few years ago, well, 2 or 3 years ago, and these ones are more recent ones. My Mathematica license has actually run out now, so I need to contact Wolfram to see if I'm able to get that renewed. But I have a few simulations here, and also you can see the papers that I've written. I wrote 2 papers since I was at the Wolfram Summer School, and I do have more resources, more information on this, more results, but I need to get my license back so that people can see that. Anyway, the purpose of this video is to really explain why I'm looking into the system that I am, and where it comes from, what the motivation behind it is, and also the details of the system. So the name that I've given to my system is the SERD model, and I call it the SERD model because really that represents Space Element Reduction Duplication, and I'll go into this in a bit more detail in a second. Firstly, I want to provide a little bit of background to what we're actually doing here. So what we know about physics at the moment is we have a theory of a quantum theory of the standard model. We have these particles that exist within the standard model, and we understand that the universe itself is non-deterministic. You can't know the position and momentum of a particle at the same time. You can't predict exactly where a particle is going to be. You can only work out a probability of where it might exist, or a probability amplitude. So everything is kind of fuzzy until you observe it. And then when you observe it, there's a particular reality that manifests itself, and then after that, everything kind of goes back to this sort of probability haziness. And then we also have the theory of gravity that describes the structure of space-time on a much larger scale. Now, one of the problems we face is that we don't really have an understanding of what governs the dynamics of physical systems at the most fundamental level. What I mean by that is we might be able to predict that a particle has a certain momentum. We might be able to say, okay, there's some forces involved. and describe the evolution of the probability distributions of the system. However, we don't really understand why particles move, or why what is a photon, for example. What actually is a photon, or what actually is a particle, right? We have ideas or systems that models that can describe this mathematically, but actually on a conceptual level we don't really understand. Another way of putting it is, if there's a probability that a particle might exist on one side of a wave function, and there's a probability that it might exist on the other, and then we observe the particle, let's say we have the wave function looks like this, and it's almost, and when we observe the particle, we see that it then after the observation, it's on the right hand side here, and we get this kind of collapse of the wave function. Why does that happen? Why does it exist on this side, right? What is the system underlying the dynamics of the particle that results in it existing on this side? Now, we also have this problem that there's massive mathematical inconsistencies between our quantum theory of the universe and our general relativity theory of gravity. And many people have the idea that the solutions to this may rise out of considering a discretization of space-time. That actually the idea that space is sort of you can zoom into it infinitely is actually not the case, and that actually if you zoom in far enough to space, you actually get to a finite smallest division of space. And you might refer to that as a space atom or a space element. And there's various theories that suggest that this may be the case. So, you can imagine that you have a particle here, and then, instead of it being sort of empty space in between these particles, there's some kind of granular structure of space atoms in between them. And then you could imagine that the size or the proportion of that distance between those two particles could be determined by the amount of space elements or the space atoms there are between those two particles. Then also what might actually happen is you could say, okay, well, what happens if these space atoms sort of disappear, or they have some kind of dynamics that they undergo, and then that may lead to some relative motion between particles. So then the question is, okay, if there is this granular structure of space, then or granular structure of space-time, there's also the idea that time is discrete or made up of bits. And so as you progress through time, it's more like a movie where there's a series of frames, one frame followed by the next. And the sort of time difference between each frame is incredibly small. The question also arises, okay, well, what is the structure then, right? When we think about atoms in a solid, they're normally in some kind of lattice structure where there's a grid, and you can define a sort of a direction where they're all aligned. But the problem with this is that in space, no direction is favored, right? In the case of a lattice, there's always a direction that the lattice is facing, whereas in space, there doesn't appear to be any appearance of some kind of lattice structure of space. So, for example, if an atom was to move in this direction along the lattice, it would supposedly move quicker than it would move along this side of the lattice, because the same distance, in order to traverse the same distance, it would have to traverse less space atoms. So the question then is, what is the structure of this system? What are its dynamics? And what causes it in the first place? There's one major difference with the approach that we're taking here with this investigation into these discrete systems that run on a computer, and then we look to see whether there's any comparable behavior with physical systems, and the normal approach of creating a model and investigating using experiments. So in high energy physics, we're looking at trying to move closer to a unification theory by increasing the energies of our experiments. And what this does is it gets you closer and closer to the high energy state that existed moments after the Big Bang. And so you can imagine it like if this is the beginning of the universe, or if this is the singularity at the start of the Big Bang, and we have this period of inflation afterwards, the current high energy experiments are pushing the boundary in this direction. So we're trying to find out, if this is time going in this direction. We're pushing back to get as close as possible to the start of the universe, to understand what the conditions were and how things behaved, and in a sense, why did the universe come into being at all. Well, in this approach, what we're doing is we're looking at systems and we're seeing whether they behave similarly to what we observe in these experiments. So it's almost as though we're taking the moment of the Big Bang and we're getting an arrow and we're pushing it back in this direction. We're trying to create possible universes that could exist and then see whether the behavior that we get out of them, or the dynamics that we see coming out of them, bears any similarities to that of the universe. So the system that I'm looking into had a bit of a philosophical background, or a bit of a philosophical motivation to it, and I've been looking into it for several years now. So I'll go into a little bit of explanation of that now. So the motivation of this system that I'm investigating really stemmed from considering the following question: what caused the universe to exist in the first place? Well, this is quite a deep question, obviously, but the result that I came to was that obviously everything within the universe that exists within space and time that we know of requires some cause for it to exist. Every moment in time, there is a state of matter, a state of the universe, which requires some moment before it to exist. So the idea of an initial moment in time is kind of paradoxical. So the solution that I came to really stemmed from considering another question: what can exist without a cause? Because what can exist without a cause surely will exist. It doesn't require a cause, so it would exist. But think about that for a second. What can exist without a cause? Everything that we know of in our universe requires some cause for it to exist. And the conclusion that I came to was that nothingness is what can exist without a cause. Nothingness is the ultimate prime mover, or the ultimate cause for the universe. So what is nothingness? Nothingness really can only be described as the absence of information. And how is information stored, as far as we know? Well, information is stored within space, stored within dimensions. So nothingness, in a sense, is the absence of dimensions. So if nothingness exists and nothingness is zero dimensions, then how can the universe exist? So the universe is made up of dimensions. How does that fit within this? Well, the answer to that stems from another question, which is, what is the size of the universe within nothingness? So this can be rephrased as another question, which is, what is the size of dimensions within nothingness? Or what is the size of dimensions within zero dimensions? Well, this is like asking, what is the size of the x-axis in the y-axis? You can't have this a proportionate size of a dimension outside of itself. Dimensions only exist within themselves. So all dimensions of space within the universe, considered within nothingness, exist as an infinitely small point. So this is nothingness. and this is everything. And this is what I call the primary singularity. So the primary singularity is the singularity that exists within nothingness. Now, there's only one primary singularity, even though within it may contain many, many multiverses, and it might be absolutely huge, but within nothingness there is no size, there is no space. And so it is just on its own, it is an indivisible point existing within the nothingness. It's also important to realize that within that point exist the dimensions, and that any time or any evolution of states within that point is eternal, because within nothingness there is no time. So from this perspective, the beginning of the universe has always happened and will always be there, and the end of the universe has always happened and will always be there. So a good analogy of this would be imagining that time is like a series of frames, and when you're inside time, you can only see the frame ahead of you, or the frame that you're in, and you progress from one frame to the next, stepping from one frame to the next. And when you see things from the perspective of nothingness, you're actually coming outside of that, so you actually see all of the frames at the same time, and you can choose where you would go in to experience time. So in a sense, the universe, time only exists within the dimensions of the universe, but the universe from the outside of the universe is eternal, and it will always be there. So we've got this structure beginning to form, this primary singularity existing within nothingness. Now, it's important to understand that the primary singularity is only one. There's only one primary singularity, and it is indivisible, because in order to divide something, you need some space, you need some dimension. And for that reason, I refer to the primary singularity as being stable. So that means that it cannot be divided. It's not separatable, and so it is stable. But we get to the next level. The next level exists within the dimensions of the primary singularity. And to consider this, it is important to realize that inside these dimensions, you can't really have a dimension existing unless there's something inside it for there to be proportion. So if all the particles in the universe disappeared, there would be nothing to define the space. You can't define something without something in the space to define the size, to define the proportion. And so in a way, just having the dimensions of the primary singularity doesn't really provide any ability for there to be information stored within the universe. And this leads to the idea that as well as the dimensions within the primary singularity, there exist further dimensions that don't have any size within the dimensions of the primary singularity, but still exist, but exist within themselves. And so what would be the size of these dimensions, these further dimensions in the primary singularity? Well, again, like how the x-axis is infinitely small in the y-axis, you would have them being infinitely small within the dimensions of the primary singularity. And this leads to the concept of the existence of a secondary singularity. This secondary singularity exists within the dimensions of the primary, and so it may undergo a interaction with those dimensions. What I mean by this is the secondary singularity can actually be split, whereas the primary singularity cannot, because the secondary singularity exists within dimensions, and so there's the possibility for it to be split in 2, in 3, in 4, into many little bits. So that's why I would say that the secondary singularity is unstable. It can be split. And it's this instability of the secondary singularity that leads to the SERD model that we are investigating here. So what we're really investigating with the SERD model is how this secondary singularity interacts with the dimensions of the primary singularity. Essentially, the secondary singularity will split in two, divided by an infinitesimal division of dimension of the primary singularity, and it will explode, more splitting, and create essentially a network. And so the SERD model is investigating this, is investigating how this secondary singularity is split and then creates a whole dynamics of this system. And so in the context of physics, what this is suggesting is that this is essentially the first moment in the Big Bang in the universe, and we are looking at the first few frames, the first few instances in time from that initial moment. And from this we get a system, and we're then trying to look and see whether we can show that there is some compatibility or some comparability with physical systems. So the first transition from this initial state is likely to be a division in one dimension of the secondary singularity by an infinitesimal division of dimension from the primary singularity. This introduces the two fundamental constituents of the SERD model, which essentially are point particles, which are the splitting children, if you were, of the secondary singularity. These here, so we were going to refer to them as PP, or point particles. And then there's the space elements, which are the divisions between the point particles. I think it's important to make the point that this system is essentially a network substitution system, and I know that many people, particularly on the Wolfram Physics project, are working on systems that are very, very similar to this, or maybe even the same as this. And that's really the reason why I'm making this video, to connect with people, to communicate my ideas, and hopefully to build up a network of people that I'm working with on this project or on other projects similar to this. So let's dive right in. A split is where a point particle splits in two, essentially, divided by a single space element. This may happen in a particular time step. This is a merge where you have a string of space elements between two point particles, and they would then, in the same time step, all disappear, and you would end up with two space elements, so 2 point particles merging to form one. Space elements may also undergo some actions, so that they may duplicate, which means a space element initially being one space element will undergo a time step and become two space elements. And a reduction is where a single space element reduces to form one space element. In this sense, a merge is just a reduction of all of the space elements between 2 point particles in one time step. So you can imagine you have a point particle, a split occurs, and then a series of duplications occur, which causes in one dimension the 2 point particles to be split by a number of space elements. I call the string of space elements between any 2 point particles an interaction edge. So as one moment in time progresses to the next moment in time, every element in the system, or every space element or point particle in the system, may or may not undergo one of these actions. And so in a sense, this corresponds to a multi-way system, where every possible combination of actions happening could be realized. And this has connections to the idea of the quantum multiverse idea, that many different possible quantum realities may be manifested in different possible universes. And so this is very along the same lines as what's being said in the Wolfram Physics project. So you can imagine this situation where the secondary singularity is a bit unstable, and it's split by an infinitesimal division of the dimensions of the primary singularity, and then that infinitesimal division or space element doesn't really know whether it's 1, 2, or 0, and so it may duplicate, and then following a number of duplications may turn into eventually a sort of a string of space elements between these 2 point particles. Now, but what happens when a point particle splits? What happens to the interaction edge? Well, this then leads to the next idea that actually the system becomes a graph of sorts, or a graph of sorts. Now, initially I thought that this structure would be a complete graph or a fully connected network, but recently I've realized that that's not quite how this works. So I will give the description now. Now, I haven't fully investigated the system. I haven't actually managed to create a full model describing every single aspect of the system, but I will explain all of the aspects of the system here. What I initially thought when a split occurred in this system, what happened was that the interaction edges that were touching that point particle that split would be cloned. That means they'd be created a sort of a duplicate copy of that interaction edge. Now, I've realized now that actually the answer is a little bit more subtle, and it stems from a particular idea about all of the elements in this system. Essentially, it is that all the elements in the system have a form of awareness of the system around them. That means that whenever an action occurs, like a split, a merge, a duplication, or a reduction, that information of that action will only affect those that information has reached. So what happens is when a duplication or reduction occurs, there is some information that forms some information that then propagates through the interaction edge. Remember, this is the interaction edge is dynamic, and so it will be changing with duplications, reductions happening all the time. And these what I call action wavefronts will then propagate through the system. When a split occurs as well, the information of that split also propagates through the system. So what will happen is instead of it cloning the interaction edges in one instant in time, you would have something a little bit more like this. So as you can see, there's two different representations here. One where I've drawn on the space elements, you can see the space elements, and then a split occurs, and then another one where it's just a line to represent the interaction edge. Well, when a split occurs, it essentially only passes to the first space element, and then as time progresses, this will pass down the interaction edge, essentially at a rate of 1 space element per time step. Because in the same way that essentially because the space element can only know the information that is on the space element next to it, so it passes by almost like a Mexican wave, 1 bit at a time. But it's important to remember that this is happening while the entire system is undergoing dynamical evolution. So the space elements are duplicating and reducing all the time, but then the information is also passing through it. So this is for a split, but something similar happens for duplications and reductions. So here we have the representation of a propagating duplication. Let's suppose at some point in time one of the space elements duplicates. Now in this example, to keep it simple, we're imagining that the specific case where all the other space elements don't undergo any duplications or reductions as this action wavefront, which I call it, propagates through the system. Now, on every point particle kind of has a point of view or a frame of reference of the system. So if you imagine this system is like a network, each point particle in the system has its own essentially awareness of what is going on in the system. And that corresponds to the information that has reached that point particle. So in this particular case, we have a duplication and it propagates through the system at a rate of, this information propagates through the system at a rate of one space element per time step. This is, remember, this is happening, even in this case it's happening when no space elements are duplicating or reducing, but in reality this is going to be happening when all of the other space elements are duplicating, reducing all of the time. And so it's essentially when these duplications and reductions happen, this has the effect of shifting or moving the action wavefronts. The other thing that's important to realize is that all of these duplication reductions, they're creating these action wavefronts, this information that propagates through the system, and as this information reaches another bit of information, another action wavefront, it will actually superimpose on that. So if you have a duplication that comes in contact with a reduction, or let's say a duplication, information of a duplication reaches a space element that then reduces, that reduction then cancels out the duplication. So essentially you could imagine this as when a reduction occurs, the information for that would be -1, and for a duplication the information for that would be +1. In the system that I'm looking at, I actually use 0 to represent a duplication, reduction, and 2 to represent a duplication. And so then you can just add everything up and you get the number of space elements. But at the moment I'm waiting for my hopefully to get my mathematical license back, so that then I can actually show you some of this some of the work that I've done. But at the moment we're stuck to working with diagrams. But hopefully you get some idea of what this system really is. So it's highly dynamic. You've got all of these space elements duplicating and reducing, each one of them creating information that then propagates through the system, superimposing on all the other information that's propagating through the system. So one version of the system that I've been looking into in particular is one where splitting is not considered. And this is just because it makes the computation a lot easier. When you're considering splitting, you have to think about how the interaction edges are going to evolve, how they're going to be affected by the splitting, how do you store the information that is on the interaction edges as a split affects the interaction edge. Now, that may be because the interaction edge is then cloned, and then that will change the size of the array that is storing the information on the interaction edge, or on all of the interaction edges, or it may be that as you split, it then splits the interaction edge in two, and then there's some point where there is a connection halfway along the interaction edge, or there might be multiple connections, and then those connections are moving dynamically through the system while the whole interaction edge is changing. So it's quite complicated to code that. So to investigate this system, I've kept the number of point particles constant, and in that system it looks a lot like a complete graph, where the edges of the complete graph correspond to the interaction edges. And like I said, inside those interaction edges, where we have space elements, strings of space elements that will undergo duplications and reductions in each time step. But when a duplication or reduction occurs, it then will send that information through the interaction edge like a ripple, traveling at one space element per time step. Essentially telling all the other space elements, look, I've duplicated. This is a duplication has occurred, and it sends a ripple through the interaction edge, which then reaches one of the enclosing point particles. That point particle will then be updated. It will be, hey, this is the new state of the system, and then that information will then propagate once more through the rest of the interaction edges incident on that point particle until it's reached all the point particles. So what we're building here is this system where every point particle or every vertex in the system has its own awareness or its own frame of reference, or its own reality, essentially, corresponding to where it is in the graph. So when, and you can sort of describe this mathematically, But in essence, you choose a point particle. You would call that the centralized point particle. It doesn't matter which one it is. You can choose it arbitrarily. Now, the state of the system will be determined by the information that is incident on that point particle in each moment in time. So in every time moment, there'll be a certain amount of information that would have reached that point particle. In that moment in time, it will update it from that information. And then that information essentially disappears, but it's still conserved because it has been passed to the point particle that then updates the state of the system. So the state of the system can be stored on a matrix, essentially, where each entry in the matrix corresponds to an interaction edge between 2 point particles. The rows could represent one point particle, and then the columns represent the other point particle, and all of the entries correspond to the interactions between those. So you have a matrix describing the all of the edge weights, or the edge weights that the central point particle that you've chosen is aware of. So how does this relate to space in this context? Like, how can you describe this system? Because actually, when you look at this system, each interaction edge can evolve independently, and so you can see that you would have massive violations of Euclidean geometry and violations of the triangle inequality, and so this whole system is incredibly curved. So how can we relate this to space as we see it? I mean, the universe exists within 3 dimensions. Normally when we describe space, we describe it with 3 coordinates or with polar coordinates. And normally those 3 coordinates, you have x-axis, y-axis, z-axis, and you have those points within space, and the points move within space, and there's some dynamics. How does this system that we're looking into relate to that? Well, like I said, each interaction edge is defined on a matrix. It has an edge weight, and that edge weight corresponds to the number of space elements that the central point particle that defines the state of the system is aware of. Now, space elements are a measure of spatial extent. So it sort of makes sense that the size between 2 points is somehow related to the size of the number of space elements between those 2 points. And this leads to the idea that there are essentially 2 metrics in this system. There's one metric, which is the true metric, the metric between the 2 point particles in the state graph, or the system as a whole, and then there is the distance between 2 point particles in the embedded space. So what is the embedded space? The embedded space essentially is a configuration within an XY coordinate system that is favored by the matrix, or the shape of the state graph. In essence, you can also imagine it as, if you were to imagine the system in any number of dimensions, it would be a configuration in those dimensions, or in that coordinate space, that minimizes the curvature induced by the state graph. Or if you were to imagine that the interaction edges had some amount of elasticity to them, or they sort of almost like springs, it is a system that reduces the amount of strain that the embedding the system in 2 dimensions would have on that on those interaction edges. Like I said before, the state graph, because the interaction edges evolve independently of one another, they violate the triangle inequality, and they are highly non-Euclidean, and so you can't fit this thing together easily in normal flat space. And so as a result, there is a sort of minimized configuration of this system. So there are actually a few different forms of embedding that this state graph takes in coordinate space. One of them is strain minimizing embedding, and so that's the one where you take an initial configuration and then you relax the state using a strain minimization algorithm, the iterative algorithm that minimizes the strain and creates a configuration like this. And you do it like 1,000 loops or 1,000 times, and eventually it gets to this configuration. Depending on the initial configuration, you might get slightly different orientation, and that orientation is reflected in the x-axis and reflected in the y-axis. So there's a reflection of the state graph in the x-axis, y-axis, depending on that. The other form of embedding is what I call time-iterated embedding, where you imagine that the system can only sort of iterate or relax itself once per time step, and so it's sort of lagging behind itself. One of the interesting results from this form of embedding is that the average expected velocity of the point particles is constrained to be below 1, and that was the topic of my second paper, but I actually have even more evidence supporting that now. So essentially, in that form of embedding, the velocities of the point particles is constrained to be below 1. Now that's particularly interesting because the Planck length and the Planck time, if you do the Planck length over the Planck time, you get the speed of light. And it's believed that the size of these space elements, when you extrapolate up, likely to be around about the Planck length and the Planck time. So that would imply that this sort of propagation of information at one space element per time step is approximately the speed of light, and that these point particles that essentially provide the explanation of what matter is constrained to not go faster than that speed. As well as this, there's also a definition of mass within the system that I described in the first paper that I wrote. Essentially, point particles, if the interaction edges between the 2 point particles tend to reduce more than they duplicate, this means that there's the possibility of point particle clouds forming. These essentially are clusters of point particles whereby the number of point particles and the diameter of the cluster of point particles inside the cluster, number of point particles inside the cluster and the diameter of the point particles are essentially constant. There is a balance, an equilibrium that is met. And so you end up in this situation where you have this cluster that is then moving around in the embedded space. Now, the more point particles there are within the cluster or within the point particle cloud, the more interaction edges there are on that point particle cloud. The idea is that the more point particles there is a direct correlation or direct proportion between the number of point particles in the point particle cloud and the effective mass of the particle. So, for example, this point particle cloud would be more massive than a point particle, just an individual point particle, or a point particle cloud consisting of 3 point particles. And this is essentially because you need less actions, less duplications and reductions to displace 1 point particle than you do to displace a cloud of point particles. An example of this would be, imagine you've got 1 point particle here, and a single duplication occurs to displace that point particle. It may move some distance here. But if you have 2 point particles and you you have a duplication that comes onto these 2 point particles, it will only be displaced half that amount because the position of the point particle cloud will be the average distance, the average position of the 2-point particles. So this is essentially the idea that masses come from from the size of these point particle clouds. All right, so to conclude, we've got this system, which is essentially a network where the vertices are point particles and the edges are interaction edges, which are strings of space elements that connect all the point particles. The space elements may duplicate or reduce, and as time evolves, the information of those duplications and reductions propagates through the interaction edges, updating the state of the system on each vertex or each point particle as that information reaches them. This information also will superimpose on the other information, and reductions will cancel out with duplications, essentially. This creates a very dynamic system that evolves. The point particles themselves can split. So you can imagine a split. As a split happens, it will sort of it will itself split the interaction edges that are incident on them. You'll get something that may look a little bit like this, with the incident interaction edges sort of being split halfway along. Bifurcated, I think maybe is the word. And so that is what happens with the splits. And then, of course, if all of the space elements between 2-point particles reduce in the same time step, that will result in a merger, which is possible. Then, of course, this system is then embedded in x number of dimensions, or n number of dimensions, 2 or 3 essentially. The reason why you might embed in 2 or 3 dimensions, I think, stems from the first few moments of the universe. So if you have a equilateral triangle with 3 sides, each with one space element, then you would have 2 dimensions. But if it then breaks the symmetry into something that might look like this, then that might be stuck in 2 dimensions. But if it was to split again into a tetrahedron, then you would be in a 3-dimensional state. That's the idea, essentially, there. You also have these point particle clouds that can emerge if the internal interaction edges reduce more than they duplicate. This can lead to particles of different masses that can interact in various different ways. The other thing that I didn't really talk about was that actually along the interaction edges, the information that propagates through the interaction edges of the duplications and reductions clusters, and you actually get essentially photons form. You get these clusters of information that sort of pile up, and then when they reach the point particle and update the system, it actually updates the system with a chunk of information. Like maybe you might have 20 duplications that all come together, or 30 reductions that come together, which causes a sort of sudden jerk in the state of the system. Yeah, so there are various ways in which this system is kind of similar to physical systems. Obviously, it's still a little bit alien, but the nice thing about this is that it emerges out of quite a simple philosophical idea. It emerges out of quite a simple idea of primary singularity of dimensions existing within nothingness, and then a secondary singularity existing within the primary, and then this interaction emerges out of that quite nicely. This is just a series of states that evolve in time. So I've got a few simulations that I've got online. I don't have a lot. Obviously, I need to renew my Mathematica license, but some of these ones here are really representing how the geometry of the embedded system evolves in time. So they're quite pretty, actually, some of them. And you can see this. So this is what's happening here is you're taking a sprinkling. You take this is essentially a single microstate path. So you imagine you have a whole bunch of a single graph that is evolving through one path, not through multiple paths like a multi-way system, just one path. And at each state, there is a characteristic geometry when that system is embedded in 2 dimensions in this case. And what we're looking at here is that geometry. And you get it by essentially taking lots of you place lots of points on the coordinate system and then just let them relax, right? So here we're taking like 1,000 points and we're just sort of letting them all relax, and you get this nice pattern which sort of represents the geometry of the system, and it evolves in quite an interesting way. There's that, and then there's also the other simulation that I have here shows the time-iterated embedding of the system. And what's interesting about this, it also has the graph of the relative average velocities of the particles. And you can see here, if you go through this, that these relative velocities, well, this one goes up by, they tend to go below 1. You see here, it jumps up when it's been observed, and then after that it goes down below 1. There is a very nice correlation to wave function collapse here. You get a probability distribution that then you can observe a particular state, and that collapses the wave function. And when you collapse the wave function after that, a short period of time, it drops below 1 again. So like I said before, 1 essentially in this case is very much like the speed of light. So there's a lot of kind of interesting stuff that emerges out of this system, and really I'm making this video to try and communicate that to people, to get it out there. I've written 2 papers, but people don't really respond to papers in the same way that they respond to a video like this, because it's much easier to access and much easier to follow. So if you have any questions, or if there's anything that you think, hey, this doesn't make sense, or you think that there's something really wrong with this system, absolutely, please get in contact. I'd love to hear from you. Or if you find it interesting and want to know a bit more, or if you have some ideas, just get in contact. I'm going to continue hopefully working on this once I renew my Mathematica license, and I hope that in the new year I will have more collaboration on this project. Okay.